Welcome back, everyone. So today our second speaker is Elias. He's a postdoc researcher of VUB and working on collective decision making. He also received his PhD in 2021. So yes, and today's topic is about delegation to AI, a new challenge for the management of global commons. So yeah, the floor is yours.
Thank you so much. So this very big title here basically means that I'm going to show you the results of some behavioral experiments I did already a little bit ago about how delegating to autonomous systems or to algorithms influences the way people make decisions in a very specific type of strategic situation. And just to give you a bit of context, when I'm talking about strategic situations, I'm generally speaking of a set of humans that are connected in a certain way, so they can interact with each other and make decisions. And even it's possible that some of these individuals are not humans. They are algorithms, autonomous systems, and AI. And they are all interacting according to some rules that we're going to call an environment. And already some years ago, in 2021, there was this very interesting paper that more or less gave rise to the Cooperative AI Foundation, where they delineated some important fields, societal fields, where AI can play an important role, from medical to robotics to many other problems. And one of the important characteristics here is that AI, which will be embedded in social systems, need to be able to cooperate with humans. And this is, of course, even more important when we are talking about critical problems for society, like climate change, pandemics, inequality. So what I'm going to talk about today will be, first, I'll try to justify or explain to you why you should care about delegation to AI, and what exactly do I mean, and what are the differences between delegating to an autonomous system to delegating to humans. Then I'll introduce the results of a specific experiment that tried to mimic some of the situations that I just mentioned, climate change, where humans make decisions involving some kind of collective risk. And finally, I'll show the results of another experiment where we introduce this idea of delegating to AI, or to an algorithm in this case. So, of course, delegation is not a new concept. In fact, in behavioral economics and economics in general, there is a very well-known framework to study it, which is called the principal-agent framework, where we have some kind of contract between the agent, the principal, and the agent, who you're delegating to. There's, of course, information asymmetry. The person making the decisions, making the actions, the agent, is going to have more information than the principal. There might be conflicting interests, and that's why you establish a set of interests and some kind of monitoring mechanism to make sure that the agent tries to achieve the objectives of the principal. If I'm moving too much, let me know. It's maybe the voice doesn't come across. The issue is that when we are talking about delegating to AI, to an autonomous machine, it's much more difficult to set in place this set of monitoring tools. And this is well explained in this book called The Alignment Problem, where now we have autonomous systems, we have machines that are so complex that not even the person who has programmed them knows exactly whether it's performed its intended task, it's solving its intended objective. So how can we actually monitor what's going on? And of course, you might think that this is something a bit far ahead, but in fact, we are already delegating a bunch of tasks to these intelligent systems, not only to these new LLMs, which are becoming very popular now, but we've been doing this a long time by using recommender systems and different types of social media, by using Google Maps to decide how to get from one location to another, And one thing that people usually don't think about is that at some point Google Maps might decide to route us through certain places where you have some specific shops. And this can, in fact, affect social dynamics. In fact, I think I'm pretty sure Google Maps already doesn't route everybody in the same way because it tries to minimize congestion. And there are even smart devices, like this smart refrigerator that you see there, that not only is able to see what is left inside of the fridge, but it learns your consumption patterns and is able to make purchases on your behalf. And the underlying question here is whether this is going to make it easier for you to change towards better behavior, better consuming behaviors, or is going to make it much more difficult. And there are several papers already from 2023 and going to this year that are claiming that this type of practice, delegation to the systems, is going to become much more common. For example, there is this article that says that even management by algorithm is going to become very common practice and critical in business decisions. And there are also other papers like this one that have performed a set of experiments and argues that humans tend to act much more prosocial when they program machines to behave on their behalf. But there are other reviews that said the opposite, that when humans interact with automated systems, they tend to act much more selfishly. So we have literature going on both sides. And in particular, there's also this very interesting article called Dishonesty in the Digital Age. I think this is just the working paper. I don't have here the final paper. But the main thing is that in this article, there's this type of experiments that they do in economics to test whether people are dishonest, which is you give them a coin and you ask them to toss this coin many times in a room and then to reveal how many times the coin was tossed. Of course, the final result should be around 50%. And what they found in this article is that if you let humans choose the medium through which to report the final result, most humans that wanted to cheat, to be dishonest, would choose to do so through an online system where the counterpart is also going to be an autonomous system, a programmed voice. So there's some kind of self-selection there. So just to summarize this part, when we're talking about delegation to AI in contrast to delegation to humans, we're talking about delegation of consideration sets, of knowledge discovery. We don't delegate often full tasks, we delegate certain parts of our daily lives, and often we are not even aware that we are doing so, like with Google Maps. People don't really think that they are giving a big part of this agency and decision making to this app. And there are a few papers that show that biased recommendations can have a big effect on the quality of our decisions. And that's why it's important that we do research in this topic. So now let me present you the initial results on a very specific experiment where we evaluate how humans, not humans and AI, how humans make decision in a task, a strategic decision-making task that involves some form of collective risk. And what we will be asking here is how do humans make decisions under this type of collective risk. And afterwards, I'll show you the results of an experiment where we force participants to delegate their decisions in the same task, and I'll show you what is the effect. So we have this collective risk dilemma, which I think the first article that introduced it was in 2008, and it has been used very often as a model for specific problems that arise in climate action and climate negotiations. Here we have a group of participants. In this case, they all receive the same endowment, 20 units at the beginning of the game. And we ask them to make discrete contributions throughout a fixed number of rounds. In each round, they can contribute 0, 2, or 4 units. And so throughout the rounds, what we see is that some people contributed more, others contributed less. So they will go home with different quantities of money because they can take home whatever is left on their pocket. However, if they have not reached a certain threshold, they have not surpassed a certain target contributions, then there is a probability that there might be a disaster and all the members of the group lose the remaining of their endowment, so they will go home with 0. And it's important to note that one of the equilibrium of this game is that if everybody, which is also the symmetric equilibrium, if everybody contributes exactly 2 in every round, then they will achieve the target exactly, and they may go home with the same amount of money. And in the first experiments that were performed in this dilemma, they found out that only when the risk was very high, 90%, groups were successful in provisioning sufficient amounts to avoid this collective disaster. But even then, only 50% of the groups managed to do so, which is a surprising result, because by theory, with 90% of risk, everybody should be contributing to achieve the target. And so we did an experiment to reproduce these results, where we have 12 groups, 72 participants. And there's all of these parameters, but the important thing, also the experiments were performed in this room. So we actually get humans in a room that interact through a computer and they cannot talk to each other. There's a specific protocol in behavior economic experiments. Everybody's anonymous and they cannot communicate. And this is what they could see on their screen. They could see their contributions in the previous round and the contributions of the other members of the group, everything always in the same order, so that they could form some kind of history and how much was left in their personal account. And if we plot the contributions, the frequency of contributions of each participant, of all participants over the number of rounds, what we see is that at the beginning of the experiment, in the first round, when they don't have any kind of information, most participants contribute 2, which, as I said before, is the quantity you have to contribute at every round to reach the target, and so that everybody goes exactly with the same amount of money home. And that's why we call this that they are trying to signal some kind of intention to cooperate. However, as time passes, we see that groups that were not successful in reaching the target start to decrease their contributions by the last round. And that's why we say that groups fail to coordinate. They are contributing only the minimum over time necessary to reach the target, and by the last round, this becomes a pure coordination game, and they fail and the groups that fail to reach the target fail to identify what the other members of the group are going to contribute. We also clustered the behaviors of this. We also tried to identify what behaviors, what strategies participants were using. And we found a set of mainly five behaviors, if I remember correctly, where we have this, most of participants are mostly playing 2 most of the time. Basically, what I'm showing here is the average contribution of the participant with respect to the contributions of the other members of the group in the previous round. And since most of the time the contributions are going to be around here, we say that these players are mostly playing 2 at every round. But we also find a smaller proportion of players that are being very reciprocal. That is, if the other members of the group contribute very little, they will also contribute very little, and they increase their contributions if the other members of the group also increase their contributions. We also have some compensatory behaviors where if the other members of the group are contributing too little, these participants will try to compensate for them. They will increase their contributions. My point appears. And then we have another group of players that we call altruistic, because they are on average contributing more than this fair amount too. And what we did is to try to build a simple multi-agent model of this system to see if we can reproduce the results of our experiments. So we consider 5 strategies: always 0, always 2, always 4. And then participants that compensate, that is, they will contribute more when the other members of the group are contributing less. And they will contribute, and then we have reciprocal participants that will only contribute if the other members of the group are also contributing. And we use a evolutionary game theoretical model where we impose a selective pressure over a population of strategies in a way that strategies that are more fit to survive tend to invade the rest of the population. However, to simplify the system, because we have a lot of strategies, also, as I mentioned, it's a model of social learning. So we assume that individuals tend to copy. That's a type of social pressure that we are applying, tend to copy those that are more successful. And it's a stochastic model. This happens with some probability. In the following way, that at a certain time t, we have a population in this state, and we take a certain individual to die, and with a certain probability, this individual is going to mutate into another strategy, and with another probability, we will select another, if there's no mutation, we'll select another individual, and with some probability proportional to the difference in fitness between the two strategies, it will copy that strategy. And that's how the population updates over time. Sorry, the slides are going a bit slow now. Yeah. However, these types of models tend to grow in complexity with the number of strategies, and can already with 5 strategies, we have a very, very big system. So what we will do is to assume that mutation is very small. So there is little enough variation in these strategies that the edges of the system simplex that defines the dynamics become absorbance states. That is, after some x time, the system is always going to go to one monomorphic population where every individual in the population adopts the same strategy. And so what we're going to be interested is in calculating the fixation probability from this if you introduce a single mutant in a population of one strategy to a population of the other strategy. So how likely it is that a single mutant is going to invade that population. And there is a series of equations for that. This is not super important. It's all implemented just for a bit of advertisement in my own library, EGT Tools. But if we do this, if we calculate these fixation probabilities, then we can simplify this big Markov chain that would define the dynamics by only considering the vertices of that simplex and using the fixation probabilities normalized as the transition probabilities of this new Markov chain. And in this way, we can plot this type of dominance graph where an outgoing arrow indicates that this strategy is being dominated by this other strategy. And here what we find is that, again, in this specific case, always plane 2 is the only dominant strategy, the only strategy that doesn't have any outgoing arrow. And we are able to get a very similar result from the experiment, about 50% of success. So just to summarize, with a very simple model, we can reproduce these experiment results. And the reason I'm presenting this model is that we are going to use it now to implement this new experiment with delegation that I'll mention in a moment. So now, I said we have this treatment with only humans. And we had 72 participants. And now we'll ask participants, instead of making the decisions themselves at each round, to choose one out of these 5 behaviors that we used in our model. And these strategies will play the game for them. So they will make we are substituting several decisions throughout the game for one single decision of what strategy we're going to do. And we're going to compare what is the distribution of strategies that human chooses with the model that we had. Of course, this again is a very restricted system. We're going from a game in which you have a lot of possible decisions to one in which you only have 5 possible behaviors. So we have another treatment in which participants can customize or program their own agent to behave in the game, throughout the game for them according to a set of parameters that I will explain in a moment. And finally, we have a nudge or hybrid experiment where we have hybrid groups where 3 members of the group are humans and 3 members are agents. And I'll explain in a moment why we call this treatment nudge. So to begin, we have this delegate experiment where participants can choose 1 out of these 5 behaviors that we had in our model. Then we have the customized experiment, which is a bit more complex. Participants have to configure 5 parameters, an initial action, the action that the agent will take in the first round, and then afterwards they have to configure an action that the agent is going to compare according to a personal threshold to the contributions of the other members of the group in the previous round. And otherwise, if it's below this personal threshold, the agent is going to contribute AB. And if it's in the middle, it's going to contribute AM. This seems very complicated, but again, we can classify these agents into cooperate if they're mostly playing 2 into the fact, they're mostly playing 0, or reciprocate and compensate if they are contributing more above or below this personal threshold. And once more, we force participants that after they make the single decision of the agent they're going to delegate to, that they observe what's happening throughout the game, because afterwards we're going to ask them a few questions. And finally, we have this nudge experiment, and the reason we called it nudge is because the behaviors of the agents that are sampled into these hybrid groups are taken from the groups that were successful in this customized experiment. So these are actually agents that were programmed by the humans in the previous experiment. And we expected that these behaviors would have some characteristics that would nudge participants to cooperate more. A spoiler, that was not the case. Also, we always showed in the same order to participants the decisions of humans and decisions of agents, but we never told them who were agents and who were humans. We only used this after the experiment finishes. We asked them to see if they could identify, and they simply couldn't figure out who were humans or who were agents. And so in our first experiment, we had about 70%, 67% of success. And in the delegation experiments, we increase to about 87% of success, while in the nudge experiment, this was not the case. And so let's try to go a little bit further into the strategies that humans select to try to understand why this is happening. So the first thing that we observe when we compare our theoretical model taken from the previous experiment to what humans are actually selecting is that humans tend to select much more often behaviors that are good or prosocial. That is, behaviors that are that aim at solving this collective problem. They select much less often than our model predicted this always 0 behavior. Now, again, you may say that this is because we have a very small set of options. So let's see what happened in the customized experiment. Of course, it's a much more, the set of behaviors is much larger, so it's much more difficult to classify them. So we'll use this personal threshold to be able to do that. We'll say that only, on average, most people selected personal threshold of 12. Basically, if every other member of the group contributed 2, that will be 10. That's why they select a value that is close. I actually expected them to select this personal threshold 10, but most people selected 12, and then they configured the other parameters in a way that that matches exactly what I expected them to do. It's just that they thought in a different way. And what we will say that only when this personal threshold is very small or is very large, these agents are not going to display conditional behaviors. And that's because the conditional will almost never occur during the experiment. So they will only display always 0, always 2, or always 4 behaviors. And only when the threshold is in these intermediary values between 8 and 14, we say that there can be reciprocate and compensate strategies. Still, the number of behaviors is quite big, but we can classify them into compensatory, which now are the majority. About 41% of the participants design their agents to act in a compensatory manner. So this also indicates that they want to solve the game. And about 10% of participants designed reciprocal strategies. But the most important thing is that a much smaller amount than our model predicted selected behaviors that contribute very small amounts, close to zero or simply much smaller than the fair amount. So again, we see that by forcing participants to make the decision on how they should play the game before the game starts, so basically delegating their decisions to these behaviors, somehow this acts as a commitment device. It forces them to continue with their initial intention to cooperate, which we saw in the human experiment. In the first round, they signaled that they wanted to cooperate, and we force them to continue with this throughout the experiment. Thus, it increases group success. And what we saw however, as I said, in the hybrid experiment, this was not the case. And in fact, when we look again at the frequency, again, I'm plotting the frequency of each possible of the three actions throughout time, we see that, again, both successful and unsuccessful groups in the nudge treatment still start with an intention to cooperate. They start by playing 2. But we see that they both play after half of the game, more often the action 0 and more often action 4. And what we see, in fact, when we look at the distribution of final payoffs, is that there's much more variance in this distribution. And one interesting thing that we're trying to follow up with a new experiment that I'm not presenting here is that when you plot the average contribution of participants throughout time, we see that successful groups, the decisions of humans and the agents were synchronized from the first round, while in unsuccessful groups, they were not. They unsynchronized by the last round. So again, another hypothesis that we have is that we either need some kind of communication mechanism or a way to synchronize the decisions of humans and agents so that they can be successful. Finally, at the end of the experiment, we asked participants whether, if they had the opportunity to play the game again, they would choose to delegate or prefer to play the game themselves. Now, you have to remember that participants made one decision, and then we asked them to see what was happening throughout the game, and this takes a little bit of time. So most participants said in both cases that they would prefer to play the game themselves. However, we do see that when humans retain a little bit of agency, when they are able to customize their agents, they are willing to delegate more often. Another interesting result is that in this hybrid experiment, at the end of the experiment, we asked participants who contributed more to the collective target, who had more burden, if it was humans or agents. And in the groups that failed, 80% of the participants blamed the agents. They thought that humans made much more effort than the agents, and this was not true. But even in the successful groups, about 50% of the participants thought the humans made more contributions than AI. I mean, in this case, it's not really AI, it's a fixed algorithm. But in this case, it was even less true because around 8.5% agents actually contributed around 8.5% more than humans. So this is another important thing to take into account when we design the systems, that there are some, at least for the moment, this evolves through time, some inherent biases against AI, as the review I showed earlier indicates. Often humans will, when interacting with these machines, will act also more selfishly because they expect these machines to interact selfishly. So yeah, again, this is, as a summary now, it's important to take that into account when designing systems. But one very interesting thing that we followed already with a paper that I'm not presenting here, that should be published soon in PNAS, and with some other experiments that I have now, is that this delegation mechanism that we have here works as a commitment device. Just by, if we understand that in a specific coordination task, humans or most of the participants tend to have an intention to select a cooperative option, then it's a good idea to try to find a mechanism that forces them to keep with this cooperative option. Yeah, thank you very much. I'll be happy to answer any questions.
Thank you very much for the nice presentation. Any question?
Thanks. How do you then think that we should move forward? Because you say maybe people are still suspicious of delegating their actions to AI or just an agent, because they might reason that they are more selfish, so they become more selfish themselves. What do you think should be done next? Like, is there like social awareness that's necessary, or should we build?
I mean, first you need, another thing that we didn't have in these experiments we are doing now is to measure social preferences, because different types of people may regard agents or other humans in different ways. But in particular, social norms are something that evolve and change. And now that we see that humans are interacting way more, particularly with LLMs, this experiment was done, I think, 3 years ago. There might be a different social norm. So I think it's important to measure the prevalent social norm and try to act upon that. That's probably the best solution.
Do you think that it will change if you do the same test, by example, in South America, in United States, in Europe, in Japan, in different areas of the world, because the mindset of the people are different?
In fact, I'm going in a month to Japan to run an experiment there. What we've been seeing, there's already been some other experiments also that look at facial expressions of an avatar and how people regard them. And in Japan, people tend to cooperate much more with machines. I mean, it's part of, there's a very specific social norm there. This might, in the future, move to Europe as well and to other parts of the world. But it's very interesting how experiments that were very uncooperative, and there's this paper from Salsamelo where he compares behaviors, how participants act or cooperate with an avatar, a virtual avatar in the US and in Japan. And well, there's quite a bit of defection in the US. In Japan, there's huge amounts of cooperation.
So if I understood well, the people are more interested by when they can choose the parameter of the agent or play with the parameter.
I think this was a very limited experiment, but now I'm designing one in which I'm varying agency much more. I think the important factor is agency, is how much control do you still retain of your decisions. In this experiment, for example, you are forced to delegate, and you can only do this once. So you're giving away all your agency. By customizing, you retain a little bit of control because you can decide with a little bit more of granularity the behavior. But what would happen if you can regain control at every round or at every X amount of time? I think controlling this agency factor is what's important.
That made me think about a research made of the implementation of AI in the industries with the workers, and the workers were not really happy because they didn't have the control of it. And I think that it could be that if you give the ability to the workers to set up their own agent, maybe they will be more happy.
Exactly, they don't have to control everything. It's still an open question of depending on specific behavior profiles, how much agency are they willing to retain. But you need to give at least some sort of control or some way to embed your social preferences, your risk preferences into a specific autonomous system that is going to behave on your behalf. Mm-hmm. Of course, then there's also the question of how this agency plays a role and how humans shape the blame if there is a problem. Because we know that this happens also when humans delegate to other humans, we often use this to shift the blame of anything that may happen. But if you're retaining part of control, this may not happen in the same way, which could be interesting, in fact. So I think there's still a lot of research to be done, but I think looking at how much agency and function of specific behavior profile should be retained is important.
Any other question? Okay, thank you, Elias.
Thank you.